Hi everyone, Lloyd Reber here again with our next example of using Excel to compute some statistics. In this video we compute the first of 3 inferential statistics covered in the course and the first of 2 t-tests, namely the t-test for a correlated samples design, also known as a dependent t-test. To begin, I suggest you fasten your seatbelt and put your tray in the locked upright position because you need to be ready for some mild turbulence that will take the form of some mental gymnastics. Rest assured, however, that computing a t-test is based on some computations that you have already done. And if you have completed the previous videos and saved your Excel spreadsheets along the way, you really don't have that many steps to complete. When done, I think you'll say, wow, I can't believe how few computations I actually did in this example. Remember, I've designed this course for mere mortals, so the route I've mapped out for us, though a little bumpy, will get us all there in one piece. I'm going to start with an explanation of the formula, and I will show how everything is actually based on n, or the total number of participants, the standard deviation for each of the 2 data sets, and Pearson R, the correlation coefficient we computed in the previous video showing the relationship between the 2 data sets. So let's get started, and don't worry, a beverage of your choice and a bag of peanuts will be served after we reach cruising altitude. So at the top we have the 2 formulas for the 2 t-tests we are going to be computing. Again, in this video I'm just going to be showing you how to compute a t-test between correlated samples. But I wanted to show you at the very beginning some relationships between the 2 formulas. Now you can see that I've dimmed out the details about what we're going to be talking about in a few minutes, but I wanted to point out that we have some very familiar friends coming up here. We have n, the total number of participants. We have the standard deviations of both of the data sets, and we have the Pearson R, the correlation coefficient that we computed in the last video. So everything we're about to talk about, I want you to remember, is based on these calculations that we've already performed. So as we look at the formulas, we can see that a t-test is a difference between means divided by something called the standard error of a difference. So in the numerator we have the difference between the means. We have x bar minus y bar. X bar, of course, being the mean of the first data set, and y bar being the mean of the second data set. So I think we're very familiar with that, and that looks like a very easy computation to do. Let's take a look at the denominator. As you can see, in both cases the denominator is called the standard error of a difference. And yes, this is a new term. So if they're both a standard error of a difference, why do they look different? Well, it's because in the formula on the left, it's really called the standard error of a difference between correlated means, whereas on the right, it's the standard error of a difference between means. So this subtle difference is actually very important. If you think about what a correlated samples design is all about, it's really about a group of people who have been given 2 measures. So we have 2 data sets, but each pair of data, much like with the Pearson R, they are going to be related because they are coming from the same person. But when we get to the formula for a t-test between independent samples, we are going to have 2 separate groups, or 2 samples, where each sample consists of a completely different set of people. So throughout this explanation, I'll continue to use red to distinguish the standard error of a difference, but I'll use a circle to distinguish the standard error of a difference between correlated means, and a rectangle to show the standard error of a difference between means. So let's focus now on the left-hand side formula, the t-test between correlated samples. So how do we compute that standard error of a difference? Well, that looks pretty daunting, and you might be getting a little nervous at this point, but just relax. First, let's just take a look at it, and I want to point out something, namely that we have R. We have a Pearson R as part of the formula. And remember that we have already computed that. Now, I want to point that out because that's an important part of the formula. And after all, this is for a correlated samples design. So we have in the denominator the Pearson R because we are very interested in what is the relationship between these two data sets. Now, before we try to explain the rest of that formula, let's go and take a look at the standard error of a difference between means. So you can see again with the rectangular box, I've tried to show that connection. Now, computing the standard error of a difference between means, when I look at that, before I understand what it actually is, I want you to see that there is something in common between both of the standard errors of a difference. And there it is. So what do we have going on there? Well, we have the square root of s sub x bar squared plus s sub y bar squared. Well, I just want to point out that s sub x bar is also known as the standard error of the mean. Again, a new term. But I want you to see that relationship between these two formula. Now let's go a little bit further, and I think you'll start to relax as you begin to see where this is all heading. So how to compute that? If we go a little bit further, we begin to see some familiar statistics that we have computed in the past. I want to point out that the standard error of the mean, that s sub x bar, is really nothing more than the standard deviation of the first data set divided by the square root of the total number of participants in the first data set. So we will be using that in different parts of the formula. As you can see on the left, we are going to be squaring that. And the same holds now true for the standard error of the mean for the second data set, s sub y bar. And again, we will be squaring that in a couple of places in the formula. So I hope you can see that even though it looks a little daunting, we have some mathematical symbolism that can really get in the way of understanding, but it's going to be pretty straightforward once we move to Excel, because we will be using n, the total number of participants. We will be using the standard deviations that we've already computed, and we will be using that Pearson R that we have already computed as well. Okay, let's move back to Excel. A reminder that I will be talking rather quickly, so be sure to use the pause and rewind controls as needed. A reminder also that I'm using the Macintosh Excel 2011 version, so if you are not, then you'll need to translate my actions for the particular version you are using. First step is to open the spreadsheet that we saved at the end of the last video. Mine was titled Reber-Correlation. And then we're going to save this with a new name. So I'm going to go up to File, come down to Save As, and I created a new folder in my course folder called Inferential Statistics, and that's where I want to save this. And I suggest we give this a name as your last name dash correlated underscore T underscore test. Even though I'm using a Macintosh, I prefer to save with a more standard format where I use underscores for spaces. Okay, be sure that it's going to the right folder, then click Save. The next step is to use our imaginations. You see, we're not going to change any of the numbers, but we have to imagine a completely different context in which the numbers were derived. So instead of the general survey and the course survey that we used in the correlation tutorial, we are going to imagine an entirely different context. We're going to imagine that we are using a one-group pretest post-test design. Recall from the presentation about inferential statistics that this is a design where you would select a group of people at random from your population, give them a pretest, and then have them go through some sort of treatment or intervention, such as a training program. And then you would give them a post-test, and the post-test would be exactly the same as the pretest. And you wind up with 2 scores. And what we're interested in is whether there has been a significant increase from the pretest to the post-test within this group. So let's go and change some labeling. Let me go and click on General Survey, and in place of it I'm going to type pretest. And I'm going to go and click on Core Survey and type post-test. So a very small change in my labeling, but a very big conceptual change in terms of where the data have come from. Next, let's change the layout of our spreadsheet a little bit. We are going to be computing a t-test. As we know, we're going to have a numerator divided by a denominator to get the t-value. So let's go over here to column L, and we'll come down to the same row as we have some other labels, and I'm going to type in t num for numerator. Press return. Then I'm going to come down and click on this cell in the same row as I have the labels for standard deviation, and I'm going to type t denom for denominator. Press return. Finally, I'll come down to the same row as I have the label for R, and I will type t value and press return. I like the divide and conquer strategy, and I'll be using it throughout this video tutorial. Let's go and consult the formula to see what we do next. Well, looking at the formula for a t-test between correlated samples, I think we should start with the numerator. So we have x bar minus y bar, or the mean of the pretest minus the mean of the post-test. Let's click in the cell right below t num, and we enter an equal sign. So let's go now and click on the mean of the pretest minus the mean of the post-test and press return. Alright, good start. I suggest we go and do a save. Let's go back to the formula. Well, we need to start attacking that denominator, but let's use the divide and conquer strategy, and we'll begin by focusing on the standard error of the mean for the pretest. Now, we'll use the term S sub x bar, because that will be a little bit more descriptive, especially in our spreadsheet. As you can see, that is going to be calculated by taking the standard deviation of the pretest and dividing by the square root of the number of participants in the pretest. It's always good to start with a label, so I'm going to go over here to column D, and I'm going to go to the same row as I had the labels for R and T value, and I'm going to type S sub x bar. I know it looks a little weird, press return there, but it is a very good descriptor as we go and consult with the formula. Again, S sub x bar is also known as the standard error of the mean. We start the formula with an equal sign. Now we need the standard deviation, and of course we have two that we have calculated from previous videos. Recall that the first standard deviation was one that we calculated manually, and the second standard deviation was one that we let Excel calculate using its built-in standard deviation function. For reasons that I will make clear later, we're going to absolutely choose the very first standard deviation. In my case, that is D26. Now we're going to divide by the square root of n, so we hit the / square root. The square root function is sqrt parentheses, and we'll click on n that was calculated over here. which is the 10. I'll just click on the 10, close my parenthesis, and press return. So the standard error of the mean, or S sub x bar, is 1.98 for the pretest. Let's go back and check our formula. Next, we do the very same thing for the standard error of the mean for the post-test, or S sub y bar. It's the standard deviation of the post-test, again divided by the square root of the number of participants. Let's start by putting in the label in the corresponding spot in the post-test, S sub y bar. Press return. Now I'm going to take advantage of Excel by going over to the 1.98. I'm going to choose to copy that and come over to the cell right below my label, and I'm going to choose to paste that. Press return. And let's do a save. Let's click on that cell to double check to make sure everything is okay. If I go up now and click on the formula, we see, we have the standard deviation and n for the post-test. So the copy and paste worked just fine because I was using a relative reference for the two data points in that formula. Okay, let's make sure we hit the exit out X there. So we have a standard error of the mean for the post-test of 1.82. Let's go and check our formula to see what we need to do next. Well, next we need to square the standard error of the mean for both the pretest and the post-test. Well, that'll be easy to do. Let's go and do it. Let's first put in a label. Let me go over to the pretest, and I'm going to come down 2 cells from our S sub x bar. I'm going to type S sub x bar squared. Press return. To square that, all I do is enter the equal sign, click on the 1.98, then type an asterisk, then click on the 1.98 again, and press return. Let's do the same thing for the post-test. Enter the label S sub y bar squared. Press return. Then enter an equal sign. Click on the 1.82. Press an asterisk. Then click on the 1.82 again and press return. There you have it. Let's go back to our formula to see where we stand and what we need to do next. Okay, well, it looks like we have successfully computed S sub x bar and S sub y bar, the standard error of the mean of the pretest and post-test. And those values will go there in our formula. We've also computed the squares of those two calculations, and they will go right there. And of course, we have already computed R. So, I don't know about you, but I'm getting rather excited. We have everything we need to compute the denominator. So let's see how we're going to do that. Before we go back to Excel, just to make sure we are all together, let's take a look at how we're going to do this in Excel, what the formula construction will look like. And so consider these 3 parts of the denominator. And I've color-coded them to try to show the grouping. In Excel, what we're going to be doing is taking the square root of the entire thing. So you can see where I have a set of parentheses in red. Then I have this first part, the pink plus the blue. Then I'm going to subtract from that this piece in green. And that piece in green, since I have 2 multiplied by R multiplied by the 2 standard error of the means, I'm going to need to put all of that in its own set of parentheses. All right, let's go to Excel and do it. Let's go to the cell right below the label tdenom, Select that cell. We always start a new formula with an equal sign. And we're going to be taking the square root of everything, so we will put in the square root function, sqrt, and a parenthesis. The first part is going to be the s sub x bar squared. So I click on that. Plus, enter the plus sign. We now enter the s sub y bar squared. And now minus, well, let's enter another parenthesis. It is 2 times r, so enter a asterisk. Click on the r value. Then we're going to multiply that by s sub x bar. Multiply that, another asterisk, by s sub y bar. Now we need to close the parenthesis for the second, or I should say for the last part, and then close the parenthesis for the square root function. And press return. Okay, we are now getting close. Let's go and do a save. And of course the last part is simply to divide the numerator by the denominator. So let's go down to the cell below the label t value, click on it, put in an equal sign, click on t numerator, divide by, so the forward slash, enter that, and then click on the t denominator, starting with 1.57, and press return. Excellent. I have a negative 4.1400 and so on. Obviously we should do some rounding. Let's go up and do the rounding now. I'll click on the column header L, go up to Format, choose Cells, and then I'll click on the category number, and 2 decimal places would be good. Click OK. So I have a final t value rounded to negative 4.14. Okay, let's quickly go up to File and choose to save. And now let's stop a second and catch our breath. Can you feel the turbulence going away and a calmness overtaking you? You have calculated a t-test by hand. And yeah, Excel helped us out quite a bit, but we had to do it all really by hand. I think now's a really good time to stop and think about what that t value means. So the numerator was simply the x bar, or the mean of the pretest, minus the mean of the post-test. So you can see, I hope, that we have that difference or variability between the two groups represented by the numerator. Now the denominator, we really focus on the standard deviation. And that gives us an understanding of the variability within each of the two groups. The greater variability within each of the two groups, the greater the standard deviation. And the greater the standard deviation, the greater the denominator. And when the denominator gets bigger, the overall value gets smaller. The overall t value would get smaller. And think about that last part of the denominator that we were subtracting that contained r. So think about when r is greater than 0. When r is greater than 0, it is reducing the overall standard error of the difference. So it takes some mental gymnastics to see these overall relationships. But I hope you see this ratio where the numerator is about variation between the groups and the denominator being variance within each of the groups. And you're getting an overall value showing that ratio. Now we need to check our work. Excel does have something called a data analysis tool available, which contains a large assortment of statistical analyses that are not commonly found in Excel, such as the variety of t-tests and even the analysis of variance. But for some reason, Microsoft, in their infinite wisdom, decided to start charging people for that. I actually have it available on an older version of Excel, but with my Macintosh 2011 version, I don't have access to it. But I do have access to SPSS, which is a very powerful and a standard statistical software package. So I put in these scores for the pretest and the post-test, and here is what I got. So here's the output from SPSS, and we'll take a look at this in more detail in just a moment, but the main thing to look at is right here. A t-value of negative 3.928. Now wait a second, that doesn't look right. Let's go back to Excel. Our value is negative 4.14. Now you might say, Lloyd, that's pretty close. Let's call it even. Well, no, that's not good enough. As it turns out, I know exactly what's happening, and you may recall my insistence that we use the first of the two standard deviations for the pretest and also the post-test. So let's take a look to see what's going on there. Let's go and click on the standard deviation of the pretest that we used in our calculation, and let's go up and take a look at the formula. And as you can see, it's the square root of the squared deviations divided by n. A23 is n, or 10. And you may recall that there are some times when you divide by n and other times when you divide by n minus 1 when calculating a standard deviation. And to simply cut to the chase here, we should have divided by n minus 1. So what I'm going to do, and you should do this as well, is I'm going to revise this formula to show n minus 1. And it's very simple. We're just going to go right after the A23 and put in minus 1. Now we do need to put parentheses around A23 minus 1. So let's do that. Let me put one parenthesis at the end and one parenthesis at the very beginning. It's very important. Okay, press return. Let's do the same thing for the standard deviation for the post-test. Come up here to the formula, put in minus 1, and then surround that with parentheses. Press return. Let's go back and take a look at the formula again. There was actually a clue in the formula, and maybe some of you saw it, in that the standard deviation for both the pretest and the post-test was represented with S hat. And S hat is used to show that we are estimating a population's variability. When we are estimating a population's variability, we need to divide by n minus 1. Okay, back to Excel. Now that t-value still is not correct because there is still one more thing to do. I don't know if you noticed it, but our R value decreased. It went from 0.66 down to 0.60. And the reason is, and I know this is going to be as clear as mud, is that it needs to be based on the other standard deviation, namely the standard deviation based on a population, that is the one where we divide by n. And recall that the second standard deviation that we have in our spreadsheets is one that we put in to check our work, and the second one is based on the built-in function that Excel has for computing a standard deviation based on the population, which is based on dividing by n. And indeed, if I go and click on that and take a look up in the formula bar, you will see that we have that function stdev.p, p standing for population. There's another one, .s, that is based on the sample, and the .s variant would be based on having n minus 1. But again, the R value needs to be computed based on the standard deviation of a population. So we need to change our z values so that they actually point to the second standard deviation. But that's an easy fix also. Let's go to the first z-score in the pretest. Recall that R is based on the z-scores. And if I go up to my formula, I see that it is using the first standard deviation, which is in D26, and we need to make that based on the second deviation, D27. So I'm going to change the 26 to a 27 and press return, and I need to use the fill down trick to do that for all of the other z-scores. And I'll come over now to the z-score for the first score in the post-test. Again, go up to the formula. Again, change it from I26 to I27. Press return. Use the fill down technique to update all the z-scores. And as you can see, that puts our R back to 0.66. And that gives us a t-value of negative 3.93. Let's go check that against the SPSS output. Let's circle that t-value again here. Indeed, negative 3.928, rounded off to negative 3.93. We've done it. And the last thing we need to do is compute the number of degrees of freedom so that we can then check to see if our t-value is statistically significant. Well, here I am again, still in the SPSS output, and it really tells us all of those answers. For example, here we have the degrees of freedom as being 9, so you can see that computing the degrees of freedom is going to be n minus 1. And here we have the significance of this particular t-value, 0.003. So it is clearly below, much below, the significance level of 0.05. So we obviously have a statistically significant t-value. Well, let's go back to Excel and do this by hand, and then we'll look up the value and the degrees of freedom in a table for us to actually make sure that this matches the SPSS output. Let's go to the cell below the t-value, and we'll type in DF for degrees of freedom, press return, type in equal sign, click on the first n showing the 10, and then minus 1, and press return. So degrees of freedom of 9. So we now have a t-value and we have degrees of freedom. We can now go to a table and look up whether or not that t-value is significant. Let's do it. Here is a table of the t-distribution showing the critical values. I found this on the internet, and I'll share the link to it with you. There's lots of them on the internet. First, a little reminder what our value is, negative 3.93. And by the way, the negative sign is inconsequential. We really just look at the absolute value. The negative sign tells us the direction. So going from the pre-test to the post-test, if it increases during the post-test, we would have a negative sign. If it would decrease, then it would be a positive sign. But again, here we just look for the critical value. We're also going to be looking in the category called a two-tailed test. There's our probability level of 0.05. So that's the column we're going to be looking at. Our degrees of freedom are 9. So we look at the intersection, and we see the critical value is 2.262, and the absolute value of our t-value is equal to or greater than that. So yes, we have a statistically significant difference between the pretest and the post-test. So I have the grounds to make the assertion, statistically speaking, that that training, intervention, or activity had a significant impact or made a significant difference in the learning of those employees. Let's go back to Excel to wrap things up. Before I do my final save and end this session, I think I'm going to do a little bit of mop up and maybe a little bit of adjusting to my layout. For example, I see here in column I have some rounding I should still do, so I'm going to click on that, go up to Format, then Cells, then Number, and then 2 decimal places. And I see I had a little white area there, so I'm going to go and choose that light blue. And what the heck, let's go ahead and add a different color to both the column for the Pearson R and for the t-value. So I'll click on the column K, and I'll just choose a very light orange. Click on column L, and I'll choose a light green. All right, I like the way that separates those two statistics from the rest of my calculations. Let's go up and choose to do a final save. Now I know what many of you must be saying. Lloyd, I was with you all the way up to the point where you were congratulating us on computing the t-value only to tell us we were wrong. I know, computing statistics can be like that. Just when you think you are done, you check your work and you find something is amiss. But I'm actually glad we encountered that extra bit of turbulence at the end, because I think it helped to put into focus one of the subtleties of statistics. Dividing by n, or n minus 1, results in very small differences, but these differences are important. Frankly, I'm a believer in the principle that less learning occurs when everything goes too smoothly. We really learn when we have a problem and figure it out. In the next part of the course, we move on to computing a t-test for an independent samples design. However, this is going to be a statistical piece of cake, because all we have to do is two things. We will remove the part of the denominator that contains the Pearson R. In other words, we will be revising the standard error of a difference for an independent samples design. And we will need to compute a different number for the degrees of freedom. So I promise a very smooth, brief flight. Until next time.